Hello, everyone. We finally made it to organic chemistry. Hooray. I'm excited. I love OChem. Not everybody feels that way. You really kind of either really like it or you really, really, really don't like it. There's not a whole lot of neutral to organic chemistry. You guys are going to like this because we're just doing a real introduction to OChem. So there won't be much that you will have to suffer through in this exposure to organic chemistry. But of course, if you go on to take it in another class, I'll leave it up to you whether or not you like it or dislike it. I'm excited. I hope you do like it. But before we get into organic chemistry, I just wanted to go over this graphic that I found today, actually, that talks about the process of scientific publication. And I thought that this was a nice simplified way um, to put into perspective these papers that we're reading for Journal Club and using for research proposals, and just show the emphasis that is placed upon this process of publication, and just how much work it is to get something published. So let me share the screen and we'll dive right in. So, oh, come on, stop that. I always get that. Here we are, I think. There it is. Oh, well, all right. So, it's not super snarky, but it's kind of. Did you know that legitimate scientists publish their research in academic journals, not on YouTube? See, that's the defining, quintessential categorical difference between something that's scientific and something that is not scientific. Not that you won't find scientific aspects on YouTube, but if there's nothing to back it up in a journal of high reputation, then really, really be skeptical. Okay, getting science published is a rigorous process. Okay, and it starts, of course, with being educated, right? Having some kind of formal education, which you guys are in this process right now. And once you attain that, then you need to design your experiments, right? You need to analyze those experiments and then make graphical representations of your results. And then you, of course, hop on the laptop or desktop and you write up your paper and you submit it, and you get all kinds of revisions and changes that should be made or things that should be added. And finally, if you're lucky, and not just luck, of course, but you're hardworking, then you get your work published. Oh, come on. So step one, you get an education, right? So you get a bachelor's. You can certainly publish with a bachelor's. You can work in a lab as a technician, but more and more is requiring to get a master's or even a PhD, or even a PhD plus at least one postdoc position after that, to really get your chops in the whole scientific arena. And then once you've done one of these things here, then you can really get into it. And that comes down to conducting the research, right? So this is what you guys are kind of doing right now. Grant writing, right? That's your proposal, your research proposal. You can't do research without money. You got to have money. It's expensive. And if you get a job in academia and you get to start your lab, you will get a startup package that the university will give you to kind of get started, order the reagents and the equipment that you need, hire a few um, lab techs, get some grad students interested, but then if you're going to be a principal investigator and have your own lab, you're basically just going to write grants all the time. Yes, you'll oversee your minions, but for the most part, you are trying to bring in money, and of course, then write papers. Um, and so you do your grant writing, but to write an effective grant, you have to have a very strong literature review to show that you know what's going on in the field that you're proposing to go into and asking for money to go into, right? You have to show that you have a command of knowledge of that arena so that you're not duplicating something that's already been done, or that your whole rationale or your approach is garbage, right? And so that's what I'm hoping you guys are doing now with your research proposal, that yes, you have the paper that you picked for Journal Club as your starting point, but that you're constantly looking at other papers in the area to see what's being done, to see how you can add and build upon your ideas. And once you get a decent, well, I won't even say, I hate to say decent, once you have a well-established foundation based on what's been published before you, then you go to work. And then you get your data and you graph it, and then you essentially you go to the next step. You write it up. You write up your results. And in your results, you have to have a thorough review of other studies, right? So in your proposal, same thing. You have to provide a rationale for what you're doing. And to do that, you have to thoroughly review what else has been done in your field. You have to demonstrate that you have a command for for that knowledge base, and that you know everything about it. And then you have to write detailed methods that other scientists can follow and replicate. Okay. And so that's again what you guys are writing for your proposal. You're going to have a methods section where you are writing out the steps that you're going to take to address your question and your hypothesis. It's got to be logical, it's got to be concise, but it's got to be easy to read. It's got to be easy to follow, right? So that way, it's not just some muckety muck that is confusing and hard to replicate. Because the whole point of finding something that's scientific is showing that it has reproducibility. If it can't be replicated, that's not a good sign. And so your methods are your is your approach to answering your questions, the experiments that you do and how you do them. All right. And these don't have to be experiments that you come up with all on your own. They can be methods taken from other papers, other experiments other people have done, just in a slightly different context. You might be tweaking it to, answer, use that method in some different system or some slightly different system, right? It doesn't have to be grandiose. And then, of course, you're going to have figures and tables, and you're going to hopefully apply statistics to things so that it's robust. And then you submit your journal. Okay, and once you do that, you have to make sure that you're submitting it to a reputable journal. Right? There are some predatory journals, as they're called, that really take in any kind of you know fake, or I mean, fake is, I guess there are some, yes, there are some journals that will publish straight up fake stuff, or certainly very low quality science, meaning not rigorous. So maybe the controls aren't there, or maybe the sample size is really low, or maybe the interpretations are kind of more hand waving than being backed up by evidence. You don't want to do that, right? You don't want your paper to be published in those journals, because then you get a reputation of doing bad science. You want to make sure that the journal you submit your paper to is a trusted source. Okay, has a good reputation, has a good impact factor. So not all, but most reputable journals are going to have some kind of impact factor, which shows how important the publications coming out of that journal are to the scientific community and even the world at large. Here we go. So you submit it to the journal of interest, and I mean, you always shoot high, right? You always try and submit it to a journal that you think is going to be either the highest, like Science or Nature, or something that's going to be higher than what's probably going to publish your paper. And then just give it a shot. Don't lowball yourself. But you submit it, and then the journal of the editors looks it over and decides whether or not it meets the basic quality standards for the journal. And they'll get back to you and they'll say, you might actually want to try and submit this to some other journal, and they might give you an example. So like in my case, it was the Journal of Virology is a much more, it has a higher impact factor than Virology Journal. So you submit to Journal of Virology, and they either say, yeah, that's great, we'll put it into peer review, or they'll say, I think this would be more appropriate for Virology Journal. Okay. Something like Science. So again, I've made you guys go and get science references before. Keep in mind, 80% of the papers are rejected from Science, at least. So that's a top tier journal, right? That's the Harvard of, or Stanford or whatever of scientific magazines. Let's say the editor says, yes, let's put it into peer review. Then he's going to, or she is going to pick a group of scientists to critique your paper, usually 2 or 3. And these are going to be scientists that are in the same field or a very similar field to you, hence your peer. And it says this process is often double-blinded, but I don't think that's the case. I tend to disagree with that. It's usually just blinded, meaning that you don't know the reviewers, but they know you. And I think that there are inherent issues with that process. It should be double-blinded. The reviewer shouldn't know who's submitting it, because oftentimes, if they've never heard of you, they tend to be skeptical. Whereas if you have a highly successful scientist who has a track record, reviewers tend to look over certain things and be less skeptical because of their reputation. And so ideally you have it double-blinded so that no one knows where it's coming from. And it's an imperfect process. You guys are going to be critiquing your peers' proposals, and I'm planning to blind the proposals, but certainly you might be able to guess whose proposal it is if you happen to be in the same journal club and you recognize, the topic. But we'll try to keep it as anonymous as possible. Then you get a first decision, right? So the peer reviewers will reach some decision collectively, and they'll either reject your paper outright, or more often than not, if you've really kind of targeted to the right journal, they'll say, okay, it needs some major revisions. So you need to add some experiments, or redo some experiments, or add in some more citations. A lot of times, because they're your peers and they're in the similar field, they'll say, well, you didn't mention this one paper that came out that really addressed this topic. And it always more than likely happens to be a paper that they've published. Or maybe it's just some minor revisions. That's nice. You just maybe make a few edits here and there. Very rarely do you get to step forward, they just outright accept it without any kind of changes. Okay. I mean, even the most successful scientists with a long track record of publications and polished and have been doing this forever. It's very, very rare that it passes peer review without any type of revision. Okay, and that's important. I want you guys to know that this process isn't something that's just written to perfection and just happens to get approved and published. And I want you to know that for two reasons. One, I don't want you to get discouraged when doing this process yourself. Know that even the experts and professionals have to work at this, right? And I also want you to know this so that you can appreciate just how much effort and thought and intellect goes into publishing something to make sure that it's scientific, that it really is as rigorous as possible, that it's not just somebody's opinion, it's not just somebody's belief, it's not just somebody's anything. It's a collection of people coming together, looking over, poring over the evidence and the interpretations and making sure it's as valid as possible. Okay, and that's what makes science so awesome and so powerful. You revise it, right? Maybe you do some more experiments. Maybe you reanalyze things. And of course, you're going to rewrite a lot of things. You're going to change your discussion. You're going to add in things. You're going to, oftentimes scientists don't want to highlight the limitations and faults of their research, right? Because it's, it's just kind of nature not to shoot yourself in the foot. And the reviewers will pick holes in it and they'll find all the limitations and they'll say, you need to add those limitations to your paper. And that's why when you read your papers or other people's papers for Journal Club, you usually see some area where they talk about limitations in discussion. That's usually always at the reviewer's request, right? I'm not going to accept this paper unless you mention all the caveats. And so, it's a good thing, at the end of the day. And then you revise it, you resubmit. The average paper goes through at least 2 rounds of peer review. So you submit it, they look at it, they come back with major or minor revisions, you revise, you resubmit, and then oftentimes, if you've made them all happy enough, they will approve. And then you get published, and then you have a little celebration, and you go on and do it again. And contrary to some conspiracy theorists, scientists don't get paid for their papers. They're not in cahoots with some kind of overarching scheme to to be nefarious and harm people. Now, indirectly they might get paid because, like I said before, you get grants based on oftentimes your publication track record. So the more papers you publish and the more papers you publish in reputable journals, the more likely the government's going to give you money because they can see that you have this track record of being successful and using that money to do great science. Well, there is kind of an indirect aspect, but no one's directly paid for the papers they write. I mean, unless technically if you're a ghostwriter, then you get paid for providing a service. But scientists don't do this for the money. In fact, if you want to make a lot of money, don't be a scientist. Very few scientists make really good money. Like maybe the top execs of biotech companies and stuff. I mean, you can make a livable wage, but the idea that these scientists are all getting together to create sunscreen to give people cancer rather than the sun itself doing that, or coming up with vaccines to make a bunch of money. Really, physicians don't get paid for vaccinating either. I mean, that I don't want to get too off topic, but like, this is not some plot or scheme to rip people off or to make people unhealthy. This is a collaboration of generally speaking, altruistic intentions to make life better. And it irks me when I, you know, come across people who think otherwise. I mean, I support being skeptical about things, but you know, when you're skeptical about the skeptics, then it becomes kind of a really muddled situation. After you publish, hopefully you get a lot of citations, right? If no one cites your paper, then chances are your paper wasn't that impactful, right? If you get a bunch of citations, that means the stuff you're doing is relevant and is informative to a lot of other scientists. In fact, Dr. Anthony Fauci is one of the top cited researchers of all time because he happened to study HIV, and there's just lots of publications on that. So citations are also kind of a way to gauge your scientific prowess and the overall importance of your paper by the number of citations it gets. And you know, people use this also to try and replicate your results, and if they can't replicate it, then sometimes the paper gets retracted because you know it's was deemed unscientific, whether it was, you know, purposefully manipulated or, you know, overinterpreted. Papers can still be retracted regardless. All right, so this process is common to all scientists, whether you're an evolutionary biologist or climate scientist or a medical researcher or what have you, physics. All of this is the same process. This is the scientific process, and so it's a common denominator for all of us. And you know, really, scientists and researchers represent a small, very small percentage of the global population, less than around 1%, 0.1%, sorry. And for all intents and purposes, it's primarily a collaborative effort, right? I mean, sure, there are certain scientists that have grudges against others, and there's some competition, but for the most part, we're all trying to get at the same goal of seeking truth and shedding light on things that we didn't know. And most scientists are really happy to help other scientists. So it's a really great, fun community to be a part of. And you know, thanks to science, we have cures for diseases. We have new technologies. You know, we have a better understanding of our world and our universe, right? And so I hope that all of you, because you're taking science classes, embrace it as, you know, something that's good, something that brings hope, not something to be feared or something to hate, not something to think is out to get you or to, you know, take away your preconceived notions. It's really out there to just get a better objective understanding of our surroundings. Okay. It's demanding and rigorous, but it's rewarding, right? All the effort you put into your research proposal, all the, you know, it's hard at the time, but once you get it approved and you get that grant funded or you get that thesis approved, it's so exciting, right? You work at the bench, it's monotonous, long days, and all of a sudden you have that. I hate to say eureka because that's so overused, and no scientists really just shout out eureka in the lab. At least I've never heard that. But you know, it's a lot of hard work, and then you get a payoff every once in a while. But that payoff is so great and so elating that it's really exciting. So that's my pitch, kind of. I'm not, you know, I'm not saying you should go into science by any means, but if you're thinking about it, it's pretty cool. I like it. Let's move on to organic chemistry now. Okay. What is organic? And, you know, uh, oftentimes in today's vernacular, we think of organic as being um, produce, right? 100% USDA organic certified, right? Nice fruits and vegetables that haven't had any pesticides or artificial fertilizers or GMOs. That is oftentimes what people think of as organic. And in fact, if you look at the Merriam-Webster definition, it says organic is of relating to, yielding, or involving the use of food produced with the use of feed or fertilizer of plant or animal origin without employment of chemically formulated fertilizers, growth stimulants, antibiotics, or pesticides. Organic farming, right? So that, the, you know, ultimate dictionary just applies organic to this common uh, this common form that we think about with farming. But if you dive a little bit deeper into the Oxford Dictionary, it's much more uh, honing in on the scientific aspect of organic. Top definition: relating to or derived from living matter. Right. Organic means you have um, you know originally means that you have organs, right? You're an organism. An organism is comprised of organs. So if you're organic, you're living. And then the second, in chemistry, relating to or denoting compounds containing carbon, other than simple binary compounds and salts, and chiefly or ultimately of biological origin. See, now we're getting a little bit more specific. Now we're getting into more of what I think of when I think of organic. Third, of food or farming. So that's going back to Merriam-Webster's definition. And then in physiology, relating to a bodily organ or organs, right? So um, interestingly, what we think of as being organic, so our foods that are organic, they're organic because they are free of certain pesticides. But by chemical definition of organic, most pesticides are organic, okay? By the definition of having hydrogens and carbons or hydrocarbons, they are categorically organic. So DDT and atrazine, really, really harsh, nasty pesticides here. Those are organic molecules. Glyphosate, that is a pesticide that is contributing to, or at least strongly associated to, the decline of the bee colonies. That is an organic compound. Nicotinoids, these are organic compounds, okay? So when you think of something as being organic that you eat because it doesn't have any of these things, technically, uh, it doesn't have organic things, okay? So really, it just depends on your perspective. And so from a chemist's perspective, organic doesn't mean free from certain pesticides and artificial fertilizers and things like that. Organic means what elements are making up that molecule. Now, as I said, organic chemistry isn't for everyone. And this person here, Bejeweled Bud, was, I don't know, maybe Twitter or something, asking people for recommendations of books that made them cry. And I think she's probably looking for things like Black Beauty and whatnot. But this person, Freeze Daddy, said, organic chemistry. His OChem textbook was an example. And haha, that's funny. No laughter because I'm by myself, but maybe you got a little bit of, maybe you found the humor in that. I found the humor in that because, again, organic is one of those things that you either enjoy. It's free of math for the most part. So for those of you who don't like math, maybe you're more inclined to this branch of chemistry. Um, so I think organic chemistry is cool because all of chemistry is can be related and to everyday practical things. And certainly I've tried to illustrate some of those things, like talking about electrochemistry and how we're using our laptops in this virtual world by means to study electrochemistry, which is fueling the laptops to learn about it. But what's really cool about organic chemistry is that it's really relatable because it talks about it makes up our biochemistry, right? So we can apply it to things like when we talk about DNA and RNA, and we talk about the medicines that we come up with, and drugs, and certain aspects of neuroscience, like these neurotransmitters, noradrenaline, dopamine, and serotonin. These are all organic compounds. And interestingly, noradrenaline and dopamine are almost exactly the same. If you look at their chemical structure, there's only one difference between them: the presence of this oxygen molecule right here, or I'm sorry, oxygen atom. Right? If you add it, if you take that away, you get dopamine. If you have dopamine and you have an oxygen added to it, you have noradrenaline. Totally different. Well, not totally, but different compounds, doing different things. Noradrenaline is your fight or flight response, your adrenaline rush that you get when you're excited about something, whereas dopamine is kind of your feeling of pleasure, right? That's where you also are more susceptible to feeding into addictions from drug use, and other things, and so very different effects, and all there is one little oxygen separating those. Now serotonin is fairly different, but so organic chemistry envelops these different things that we utilize all the time on a daily basis. And if you're more in like the engineering realm, it's also that too. All of our plastics are derived from petroleum originally and have been used. I mean, think about all the different plastics that are out there. Some plastic is pliable, some plastic is very rigid, some breaks, some bends. um, for those of you who like to mountain bike or road cycle, carbon fiber frames, all of this stuff, all of these advances are made possible by the understanding of organic chemistry. Okay. So what is organic chemistry? Let's boil it down. What is it? It's the study of carbon compounds, more specifically hydrocarbons. So carbon, hydrogen bonds. Okay. The very simplest form of this is methane. Okay. So one carbon bound to 4 hydrogens. Now, you guys will remember from Chem 100 and Chem 101 that carbon is tetravalent, meaning it has 4 bonds, right? It's in group 4. And so it can form 4 bonds to be stable and happy. And that is why carbon has been the element that has made up all living things, because it has these 4 bonds. It makes it more versatile, right? Compared to something that can only bond with 3 things or 2 things. The more bonds it can have, the more versatile it can be. And interestingly, in the inorganic realm of chemistry, silicon kind of takes up that void. Silicon is also in group 4, so it can also have 4 bonds, and so silicon is comprised in many different minerals and rocks, and there's an old Star Trek episode, I think the original Star Trek, where they go to this planet, and instead of being carbon-based life forms, they're all silicon-based life forms. And so I think that their 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 technology won't work on them because it's based on the properties of carbon, which is a little bit loose. But point is, if you're a Star Wars fan, I actually like Star Wars and Star Trek both, but Star Wars is very much more of a religious thing with the Force and non-scientific midi-chlorians and stuff, whereas Star Trek really hits into much more of a scientific approach. So again, I like both. It's hard to say, I won't go into that battle in this recording by myself, but definitely Star Trek wins points for being more scientific. I'll leave it at that. Now, when we talk about what makes carbon such a good element for life, for living things, and just for all the vastly different molecules that are out there, we have to think about the Goldilocks principle. So not only does it have 4 bonds, up to 4 bonds, but the strength and weakness of those bonds are just right. Hence the Goldilocks principle, right? You don't want to form bonds that are too weak, like Pierce Brosnan's James Bond attempt. Because if your bonds are too weak, they're going to fall apart. All right? If you're using an element that makes weak bonds to comprise your DNA, you don't want your DNA falling apart because the bonds are weak, right? Conversely, you don't want your bonds to be too strong, like Daniel Craig. His James Bond is like super grizzled and almost too strong for me. Although I like him much more than Pierce Brosnan. Because then they can't form new bonds, right? They're not flexible enough to be adjustable, right? They're too rigid. What you want is something in between, right? The Goldilocks of bonds. Not too weak to fall apart, not so strong that it can't, transmute into some other molecular form. And so before we get much further, we got to do a little bit of a review on things, okay? We got to review Lewis dot structures. Remember those? Fun stuff coming back again for your enjoyment. The process, right? What do? You count the total number of valence electrons in that molecule. You then determine what is going to be your center atom. And then you replace the remaining atoms around that center atom and then position the electrons. Okay? So what I want you to do here is see if you can do these Lewis dot structures. And I thought what's going on here? And we'll see how you do. Okay. Okay. Hopefully that was a pretty simple review, and you guys got that down. I'm going to try, rather than write it on the board, I'm going to try to write it up on the screen here. So let's go back to the slide deck and see how this. We'll see how this goes. Come on. Okay, so remember, you count the total number of valence electrons. Well, how many valence electrons does H2O have? Well, first of all, hydrogen is going to have one valence electron, right? So where's my annotate? Let's do this. Okay, so hydrogen has one, but then there are two of them, right? Two hydrogens, so times 2 equals 2. And then how many valence electrons does oxygen have? It has 6. I don't know why I wrote 6 there. Well, I think I wrote 6 there because I was getting ahead of myself. Let's try that again. 2. So that means we need 8. 2 plus 6 is 8. All right, so in this case, oxygen, I like red. Oxygen is our center atom. And then we have that bound to a hydrogen. It's supposed to be dots. Right here. 2. All right, the 2 electrons represent a bond between the hydrogen and the oxygen. So now we have 2, 4. We need to add 2 more to get 6, 8. Voila. Now, for CH4, remember what that is? That is methane. And it's going to be carbon, which is going to have 4 valence electrons, and 4 hydrogens, which each have 1. So again, 8 total valence electrons, and we put carbon in the center because hydrogen can only bond to one. No. Can only bond to one thing. So let's show this bond here to this hydrogen. Right? And there are 4 of them, so 1, 2, 3, little tiny hydrogen, and 4. Okay, 4 hydrogens and poorly drawn dots, but 2, 4, 6, 8. It's all good. Then what about carbon dioxide? Well, carbon, again, 4 valence electrons. Oxygen has 6, but there are 2 of them. So that's 4 plus 6 times 2, or 4 plus 12, or 16. So I'm going to draw carbon. And we're going to make it double bond, right, to oxygen. Right? Because if we drew carbon out in the stick form, we would write it like that, right? And then put our dot. Yeah, but for the Lewis dot structure, I'm going to just, instead of drawing the double bonds, we'll draw them as these dots. Okay, I think I got 8 so far. So now what? I'm not quite there. I said that we needed 16, right? So, oh, and I forgot to put the 2 here, right? All right. And 2 on this oxygen. I feel like my dots are getting worse, not better. Okay, so now we have 2, 4, 6, 8, 10, 12, 14, 16. Done and done. NO3, well, we got N in the center, and then we have oxygen, oxygen, and oxygen. And then we add in our valence electrons. So let's see, what's nitrogen? Nitrogen is 5, and oxygen is 3 times 6. So is that 29? No, 3 times 6 is 18, so 23. Does that make sense? Let's see. Is it 5 or is it? Yeah. So yeah, let's do a single bond here. And a single bond here, because nitrogen can only have up to 3 bonds, right? So we can do double bond here. And so we have 2, 4, 6, 8. And then now this oxygen here wants to have an octet. This one, we give it an octet. And then this guy, because it has a double bond, we're just going to get 2 here like we did with carbon dioxide. And we have 2, 4, 6, 8, 10, 12, 14, 16. What did I do wrong on that one? 2, 4, 6, 8, 10, 12, 14. Oh, no, I didn't do anything wrong. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. And because there are 23, it's going to have this negative charge here. And voila. And then finally, for C2H6, we're going to draw, you're going to add that up, and that's going to be what, 2 hydrogens. So that gives you 2 times 6. That's 12 plus 6 hydrogens at 1 each. So we're shooting for 18. And I think, right? Does that make sense? Oh, yeah, C2H6. All right, so let's try this. Oh, why is it? For some reason, it's not writing. Did I lose that? Okay. Let me erase this so I have some room. Okay, so C, H. You know, I'm gonna pause it. I'm gonna write this on the board because I think that my handwriting is not going to do this justice. So So C2, so C, set this up here, H6, so 1, 2, 3, 4, 5, 6. And I know why my math was wrong, because I think I said C had 6 valence electrons. It has 4. So 4 times 2 equals 8, and 6 times 1 for hydrogen equals 6. And so that seems better. Now we have 14. Okay, so let's put it in. Just one bond. Maybe I should have just done this with all of them, because this looks much better. Oh, and then right here. Right? 2, 4, 6, 8, 10, 12, 14. Bam. Good. So that is our Lewis dot structure review. Hopefully that wasn't too painful. And let's go back now and see why we even need to do this. Why are we drudging up the past? Well, come on. Because it informs us about how molecules come together. Because they're trying to satisfy their octet, right? That's why molecules are made to begin with, to be stable. And it's good to know what these represent. So the 2 dots here represents a single bond. If you see 3 ... that's a triple bond. And 2 dots are double bonds, which we didn't do any triple bonds, but we did use single and double. And we're not really going to do a whole lot of Lewis dot structures, to be honest, but just to give you kind of a background on, how this is important, we write it out like this. Okay. Organic molecules have covalent bonds, right? Not ionic bonds. They share these electrons, and when you have something like ethane, C2H6, which is the Lewis dot structure we just drew, it's going to be carbon covalently bonded to hydrogen. Okay. And we'll get into why this is ethane and why it's eth, the prefix and the suffix. It's all designed very specific to each molecule. When a carbon binds to a more electronegative element, you get a polar covalent bond. Remember those, right? So carbon has an electronegativity of 2.5. Chlorine has an electronegativity of 3.0, and that's greater. The difference between those is greater than 0.4. So that means it's going to be a polar covalent bond. And so chloromethane or dichloromethane, those are polar molecules. And dichloromethane is a polar solvent that's used very frequently in organic chemistry and in OChem labs, because it's of the polar solvents, it's not quite as volatile as, say, something like ether. Whoops, there we go. Carbon can form multiple covalent bonds by sharing more than 2 electrons with a neighboring atom, right? So it can form, so if we had ethane, right? Here is just C2H6. So eth, what you'll come to be very familiar with is eth means 2 carbons. Meth is 1 carbon. So meth, eth, prop is 3 carbons. Eth, meth, prop, bute is 4. Prop, or pent is 5. Hex is 6, and you have sept and oct and non and deca and stuff like that. But we don't get much past hexane or hex in this class. But anyway, if we took that 2 carbons that was ethane before and we add a double bond to it, notice we lose some of our hydrogens now. Now it's no longer C2H6, it's C2H4, because carbon can only form 4 bonds, right? And now we call it ethylene, or ethene is what it's also called. And so notice it's no longer ethane, it's ethylene. If we instead change this to a triple bond between the carbons, now we lose an additional 2 hydrogens, and we have acetylene or ethyne. Ethylene, you may know, is the gas that is what leads to fruit ripening, which is why if you want to ripen stuff faster, they say you put it in a paper bag, which traps the ethylene gas in there. And so it's more concentrated, helps things ripen more quickly. Or if you don't want things to ripen so quickly, you shouldn't put certain fruits together, right? Where the gas exchange will lead to over ripening. Or if you get a bunch of bananas, a bunch meaning not like a lot of them, but like a clump of bananas, you get them home, rip them apart so that they're individual bananas, because then that there's no longer that contiguous network for the ethylene to pass through each banana. So they might ripen at slightly different rates. Whereas if you have them still on the bunch, when the first one starts to go, they'll all start to go. Acetylene, you know that from your torch, right? An acetylene torch, it's also a gas. Carbon can form single bonds, double bonds, or even triple bonds. There's also, of course, 3-dimensional space. Think Vesper, right? Carbon has 4 bonds, and that's going to have a tetrahedral formation, right? Right here. They're trying to be spaced out as far apart from each other as possible. So remember Vesper, right? We have different geometries based on the number of essentially electron groups, right? That are bound to that central atom. So in this case, when we're talking about carbon, we're talking about mostly tetrahedral formations, unless of course it gets more complex. It can form rings, and some of those rings will also be tetrahedral in shape. It's not all. But this is what we're going for, tetrahedral. And then there are different ways to write out the formulas for these different molecules. Okay, so the complete structural formula is going to let's see, my little pointer. It's going to draw out each individual element and the bond in between the elements that are bound together, right? So this would be C3H8 or propane. And so that really clearly defines everything and what's going on with this molecule. But you can condense that if you want to into a condensed structural formula where you still have kind of the elements grouped, but you don't have the bonds. So notice it's not written out C3H8, it's CH3, CH2, CH3. So it still gives you kind of the flow of how that molecule is arranged. So C3, right? This first carbon and 3 hydrogens, and then a C2, second carbon, 2 hydrogens, and then another C3, third carbon and 3 hydrogens. That's the condensed formula. You can also write the condensed structural formula with lines here, kind of that shows the bond angles and how it's actually arranged in space, right? And then there's this line angle, or also called a skeletal structure. So you just have lines that depict carbons and hydrogens, hydrocarbon bonds. Okay. So in this case, It's the same molecule for all these different ones, but this one is just 2 sticks. But those 2 sticks represent 3 carbons. Let me do my drawing here. So this implies that there's a carbon here, a carbon here, and a carbon here. And if there's no other element designated, we just assume that these carbons have hydrogens and the correct number of hydrogens to make them stable. So this end carbon here has 3 hydrogens, and this one is going to have 2, right? And then the last one is also going to have 3. And now it's starting to look a lot like the complete structural formula. Okay. Make that thick. So those are the ways that we can write these. And again, don't be confused when you see this and think that, well, there's only 2 lines, so that must be 2 carbons. That means 3. Okay. Now, we've been talking about organic molecules thus far as being hydrocarbons, but organic molecules also oftentimes have nitrogen and oxygen bound to them. All of our biomolecules are going to have, not all, but a lot of the biomolecules, our DNA, the nucleotides that make up our DNA are going to have nitrogens and oxygens on them. Okay, and it can be a carbon-nitrogen single bond, double bond, or triple bond. It can be a carbon-oxygen single or double bond, or then, of course, a carbon-hydrogen single bond. Those are the different forms that they can take in the molecule that they make up. And it turns out that organic and inorganic compounds are different in their properties. If you look at the boiling and melting points of inorganic compounds, like say salt, it's going to have a high melting and boiling point, right? If you just try and melt salt, you're going to have to put a lot of heat into it before it melts. And the inorganic compounds, if it's an ionic compound, they're going to be held together by strong electrical attractions. Whereas conversely, organic compounds are not ionic. Remember, we said they're covalent bonds. And generally speaking, they're going to have weak non-ionic intermolecular forces. You remember intermolecular forces from last quarter. Dipole, right? That kind of thing. Hydrogen bonding, big one for DNA. The organic compounds are going to tend to have a lower melting point and boiling point than inorganic compounds. So, like I said, salt needs quite a bit of heat to melt it and boil it. But think about gasoline, which is an organic compound. That is a liquid, and if you keep it at room temperature, it will actually evaporate to a certain degree. As well as, these tend to be liquids or low melting solids at room temperature. Fewer gases. Methane is a gas. Ethane, propane. The simpler the structure is, the more it lends itself to being a gas. But for the most part, they're liquids. And if you think of fats, for instance, fat is usually either a solid or a liquid. If it's a plant-based fat, it's going to be mostly a liquid, right? Think of your olive oil and canola oil and vegetable oils. Those are fats from plants, and they're liquid, right? When I try to think, so coconut oil is kind of the exception. And avocado and stuff like that, they are solid. Um, but most vegetable plant matter fats are liquids, whereas animal fats are solid. And think of butter and bacon grease. Once you cool it down, it gets that white film. I mean, I think a lot of us wish that fat could just turn to gas and then evaporate off of our bodies, but unfortunately that's not the case. And really, there's a very simple explanation to that. The fats in animals are saturated fats, meaning they don't have any double bonds. The carbon bonds are all single. Okay, so they're saturated with hydrogens, and therefore they don't have a whole lot of their fatty acid tails don't have a lot of kinks in them that are formed by the double bonds. They're pretty straight, so they can stack on top of each other and form a solid. Whereas a lot of plant fats are unsaturated fats, right? Think polyunsaturated, lots of unsaturated carbon-carbon bonds, meaning lots of double bonds. And those double bonds can then can be relinquished and form new bonds with something else like oxygen, which is why certain oils, certain liquid plant-based oils can become oxidized much more readily than saturated fats, right? You have certain, if you buy oils, you'll see that they have certain temperatures that they can be heated to. And like something like avocado oil and olive oils have higher temperature thresholds before they become rancid than like canola oil and vegetable oil. And that's because they have less double bonds than other ones. So like canola oil and vegetable oil are polyunsaturated, so they have lots of double bonds, and avocado, I think, is monounsaturated, so just one double bond. Anyway, we'll get into more of that later, but I guess I kind of got on a tangent. But again, organic molecules tend to be primarily liquids. If we look at other properties that these have, like in terms of solubility and electrical conductivity, inorganic compounds tend to dissolve in water, right? Think of salt again. And then once it does, it separates into the ions, and now that allows electrical current to pass through that liquid. Whereas organic compounds generally don't dissolve in water, right? Fats, as I just talked about, fats are oils, and oil and water don't mix, right? And they typically don't conduct electricity. Now, that doesn't mean all organic compounds are insoluble in waters. There's things like sugar and thankfully ethyl alcohol, which allows us to drink alcohol recreationally rather than having to eat it, I guess. And then if we have large molecules that have a bunch of polar groups on them, like proteins and DNA, that allows them to interact with water via dipole-dipole interactions. And so then it can dissolve in the water because of that. But generally speaking, most organic compounds don't readily dissolve in water, and that definitely has issues, right? So when we have oil spills, we get oil that goes out into the ocean, and whether it's from a leak like the BP rig, or a ship carrying oil, sinks, then you have a disaster for all the organisms that live in that water, and it's really hard to get it off, right? And certainly with drug delivery as well. If you're trying to, most medicines are organic compounds, and if they don't readily dissolve in water, how are you going to get them to the target? that you want to, considering that the human body is mostly water, right? So it makes that challenging. Examples of organic compounds. Well, lots of examples. These are just a few, really. Styrofoam. We all know styrofoam. That is, I think styrofoam was actually like a brand name, but styrofoam is actually just like Kleenex is for tissue. Styrofoam is for polystyrene. Poly meaning many. Styrene is a type of molecule, so it's just a polymer of styrene molecules chained together. Polyester is like a synthetic fiber. Polyester, many esters. We'll talk about esters in a little bit. So many ester molecules strung together. Polyurethane, stuff you put on your deck to coat it. Our DNA, our proteins, right? These are all organic compounds. Fermentation is a process of taking an organic compound, sugar, and breaking it down into a non-organic compound, carbon dioxide, and an organic compound, ethanol. And then, the keto diet, that's been kind of a diet trend the last couple of years. The result of that diet is the production of ketones. Hence the name keto diet. And we'll talk about ketones later as well. And then, like I had mentioned, fats. And these are the different fats: trans fats, saturated fat, animal fat predominantly, polyunsaturated fats, your vegetable oils, and then monounsaturated. That's just one double bond, rather than polyunsaturated having a bunch of double bonds and saturated having no double bonds. So this is just just a brief smattering of things, but things that we're all familiar with and encounter frequently, or at least infrequently. Now, we know of over 18 million organic compounds, which is just kind of mind-blowing, really, if you think about it. That's a big number. And all of them have unique chemical and physical properties, right? No two organic molecules are exactly alike. Now, there are some that are very similar, and there are some that are biomimetics, right? They mimic. You can have compounds that mimic other compounds that we use. For instance, I just finished off some coffee. Caffeine is a biomimetic in neurochemistry, and we'll talk about that later at some point. It mimics adenosine, which builds up in your brain and tells you that you're tired. But anyway, all of these molecules are different, and some are good, some are bad, and some are downright ugly, right? Some of these can be very nasty and have very bad consequences to us biologically. Some of these are what make us tick, so the spectrum is broad. Organic molecules fall under a wide breadth of being beneficial, to being harmless, to being slightly bad, to being full-on deleterious. Now, because there are so many molecules that we know of, we have to have a systematized way to describe them, so that when you're talking about some molecule with another scientist, they know exactly what you're talking about. There's very little room for ambiguity, right? And the way that we classify these molecules and name them is based on the functional groups that make up those molecules. And a functional group is an atom, or most commonly groups of atoms within a molecule that has a specific characteristic, okay, physically and chemically. And so that's what we use to classify these organic compounds into distinct families. Now, the functional groups are part of the molecule as a whole, right? The molecule itself is made up of one or more functional groups, okay? And regardless of how big that molecule is, or what what its overall properties are, the individual functional groups making up that molecule tend to behave the same way as they do in other molecules that overall have very different um, overall characteristics. So a good organic compound that has a specific functional group, that functional group is going to behave the same way as that functional group will behave in an ugly organic compound. All right. So even though the whole molecule itself may have a very different effect, the individual functional groups tend to behave similarly. Okay. And so the way we define these organic molecules is based not so much on the size of it or the complexity of the molecule itself, but the functional groups that are within it. Okay, that's how we link them together and classify them. And this is kind of the part that people that don't like organic chemistry tend to dislike. Now, it's important to note that when we talk about these molecules, complexity isn't everything. Oops, I'm going backwards. Sorry. Complexity isn't everything. Here we have ethylene, right? That you remember, C2H4, double bond. It's a carbon-carbon double bond, just 2 carbons. That's it. It's not saturated. It's unsaturated. It has a double bond. And so that means it can relinquish this bond and bind to other things. So when hydrogen gas is pumped in proximity to this molecule, it can get rid of that double bond and form bonds with hydrogens now. And now you have a slightly different molecule. You have ethane. Okay. Very simple molecule. If we take oleic acid, though, which is a much, much longer, bigger molecule, lots more carbons, and then has some oxygens in there. But like ethylene, it has this 1 carbon-carbon double bond. So we would say this is monosaturated, right? Because it's just 1 double bond. When it encounters hydrogen gas, same thing. It forms 2 bonds with hydrogen. So it's going to behave similarly. This functional group, in this case, the double bond, is going to behave similarly in a very simple molecule as it does in a very complex molecule. And now these are some of the families, and I'll go through them individually right now. The very simple family that we talk about is the alkane. The alkane is, let me get my pointer out, it's number 1. It really doesn't have a functional group. I guess you could, unless you consider carbon-carbon or carbon-hydrogen bonds, single bonds, as a functional group. So for instance, propane. Propane has 3 carbons, and they're all single bonds. And so it's written like this, remember? So carbon here, carbon here, carbon here. That's the line structure. And it has the suffix ane. So propane is an alkane with 3 carbons. Alkenes have a functional group being this double bond here. Okay? So a carbon-carbon double bond is going to be ethylene because the suffix is ene here. Okay? And eth because there are 2 carbons. Remember, meth, eth, prop, but. Prop, 3, eth, 2, ethylene because it's a double bond. If it was a single bond, it would be an alkane. It'd be called ethane. And you can write it out like this with two lines here, and then the hydrogens coming off. The third family is alkyne. So we have alkane, alkene, alkyne. Alkane, single bond, alkene, double bond, alkyne, triple bond. So acetylene or ethyne is a carbon-carbon triple bond. And again, the suffix is -ine. And this is the skeletal structure. Now, from there, it gets a little bit more complicated. We have aromatic family. Aromatic, yes, comes from aroma. These compounds tend to have a smell, some pleasant, some not pleasant. But what gives it its functional group is the presence of this 6-carbon ring with alternating double bonds. Okay, so benzene, that's the simplest version, and it does not smell good. It has this 6-carbon ring with alternating double bonds and just has hydrogens on all those carbons. That's as simple as it gets for an aromatic ring. And so this is drawing the line structure, and a lot of the compounds that you'll encounter in OChem are aromatic. So if you get nothing else out of OChem, you will get very good at drawing hexagons. There's no suffix. They range in their naming system. Benzene, there's not an "ene" suffix for aromatics. It just depends. Alkyl halides, okay? That's going to be a carbon bound to some type of halogen, whether it's fluorine, chlorine, bromine, or iodine. So ethyl chloride is going to be ethyl, right? Ethyl because 2 carbons bound to a chlorine molecule or atom. So you can draw the line structures as this with a chlorine. And they have no suffix either. Now, note, don't confuse this. Don't confuse this as propyl chloride, okay? Because I know that you could look here and say, well, I see this structure up here that looks a lot like this right here, so they must be the same thing. No, don't be confused, because when you have a line that's drawn to something else, meaning not to a hydrogen, that this bond here is not a carbon-carbon bond, okay? So what this really is showing is a carbon here and a carbon here, and this carbon is bound to a chlorine, all right? So here there was no chlorine, so we can say that these are all carbon. But here, there is something there, so we're not saying there's a carbon right here. We're showing this bond being between the carbon and the chlorine, so it's going to be not propyl chloride, ethyl chloride. Same thing with alcohol, this figure here. This isn't going to be propanol, it's going to be ethanol or ethyl alcohol. Okay, 1, 2. And then this line here is showing the bond between the oxygen and the carbon. And same down here, right, for amines, which I'll get into in just a minute. This is 1, 2, and then bam, bound to that nitrogen. So that's alkyl halides. Alcohol is a carbon bound to an oxygen, which is bound to a hydrogen, or a carbon bound to a hydroxyl group. Okay, so C2H, well, 6 hydrogens and 1 oxygen. That makes up ethanol. And the suffix is -ol. So ethanol, methanol, propanol, pentanol, etc. Ether. Ether is an oxygen surrounded by 2 carbons. So a carbon-oxygen-carbon group. That's the functional group. So for instance, diethyl ether right here, It's going to be diethyl because there are two ethyl groups, right? Two carbons, 1, 2. So that's an ethyl group because methyl, ethyl. And here's another ethyl group, 1, 2. So two ethyl groups is going to be diethyl. Diethyl ether because it's a carbon, oxygen, carbon functional group. And it looks like this. Like it looks kind of like a spider missing some legs. And no suffix. These will have different things depending on what's on the molecule. And then the last one in this slide is an amine. So that's going to be a carbon bound to a nitrogen. So ethylamine is two carbons bound to an amino group. Okay. So amine is the suffix for this functional group. Think amino acids. Amino acids are going to have carbons that are bound to nitrogens. Alrighty. So that's the first 8. Now let's get into the rest. And again, this is why some people don't like OChem, because there's memorization. 9 is aldehyde. So aldehyde is a carbon with a double bond to oxygen and then a hydrogen. So ethanol, al is the suffix. So like Paul Simon says, I can call you Betty, and Betty, if you call me, you can call me Al. We can call aldehydes Al. So acetaldehyde is the simplest version. It's going to be this functional group here, this carbon, double bond, oxygen, hydrogen, right? And then just one methyl group. That's about as simple as it gets. Okay. If you had, you know, if you had another one, that would be CH2 now, and then CH3. It'd get a little bit more complicated, but anyway, that is an aldehyde. Okay, so a carbon bound to an oxygen, double bond, and then a hydrogen. If we take that same kind of format, but instead of being bound to a hydrogen, it's bound to a carbon, now it becomes a ketone. So a ketone is a carbon double bound to oxygen with two carbons on either side of it. Acetone is the simplest ketone around. Acetone, you will know, is what makes up your fingernail polish remover. It's a great solvent. It dissolves a lot. It's good with Sharpie, getting Sharpie out of things. And the suffix for that is -one, so acetone. Carboxylic acid, again, it's the same kind of feature with carbon double bound to oxygen, but instead of having a hydrogen or a carbon, it has a hydroxyl group. So it's bound to another oxygen, which is bound to a hydrogen. And acetic acid, which is another byproduct of fermentation, can be, is the simplest carboxylic acid. So it's got that backbone, if you will, of carbon, double bound oxygen, and a hydroxyl group, and then just one methyl group here. And the suffix is ic acid. So acetic acid or benzoic acid is how we name those. Anhydride is kind of similar to ether in that it's two carbons surrounding an oxygen, right? So if we go back, if we go back to ether, right, it was COC, or carbon, oxygen, carbon. But the difference is that now the carbons have double bonds to oxygens. So COC, but now we have these double bond oxygens present. And there's really no formal suffix to that. It just depends on the molecule, again, what we call it. Ester is again similar to ether, where it's COC, but instead of having two double bonds to oxygen, right up here, it just has one. Okay, so ether is carbon, oxygen, carbon. Ester is carbon, oxygen, carbon with a single double bond oxygen. And anhydride is a carbon, oxygen, carbon with two double bond oxygens. Okay. Amides or amides are going to be similar to amines, only again, they have this carbon, oxygen double bond. So if we go back, remember amine was a carbon bound to a nitrogen. Here we have a carbon bound to a nitrogen, but it also has this oxygen, double bound to this oxygen. And amide or amide is the suffix. So acetamide is going to be the simplest version. I think all of these are basically the simplest versions of what these functional groups are. But it's going to have this, whoops, it's going to have this backbone, and then whatever else, in this case, just a methyl group. Thiol is a carbon sulfur. Disulfide is a carbon sulfur sulfur carbon, and hence di right here. And then a sulfide is just a carbon sulfur carbon. And these disulfides are particularly useful and important in biology. Now here's where I normally tell my OChem students that you should make flashcards for all of these functional groups, right? I mean, that's the easiest way to memorize these. For you guys, like I said, I'm not going to make you memorize all these groups. There's no real good way to assess that doing this virtual education platform. So, it's up to you guys. If you want to study these and memorize them because you're going to be taking OChem later, then I highly recommend you do it, because if you memorize them now, when you get into OChem, it's just going to be that much easier. Okay. And for those of you who aren't going to be taking any OChem, it's probably still a good approach to make flashcards and memorize these, because as we talk about OChem for the next couple weeks, you'll find it much more easy to navigate through the material if you recognize the difference between a ketone functional group and, say, an aldehyde. Okay, so I'm not gonna make you memorize these things, but I'll encourage it. Okay, let's clear this stuff. All right, wrapping it up here. The first four families that we discussed are only carbon and hydrogen. So alkanes is going to be a single bond between that carbon and carbon, or carbon and hydrogen. Alkenes is going to be a double bond. Alkynes is going to be a triple bond. And aromatic is going to be a six-membered ring of carbons. And that's what defines that first four families that make up that kind of group. And then the next four families are going to have single bonds also between a carbon and some electronegative atoms. So whether it's the alkyl halides that are bound to a halogen like fluorine, chlorine, bromine, iodine, or if it's an alcohol with a carbon bound to an oxygen, oxygen is then bound to the hydrogen, or ethers where you have two carbons with an oxygen in the middle, so an oxygen sandwich, or amines, carbon, nitrogen. Those are all kind of similar in that aspect. It doesn't mean that their properties are going to be more similar than the first group that I mentioned, but it's just, that's, if you want to break it down and compartmentalize these groups, this is kind of a way to think about it. Okay. And then you have the next six families that contain carbon oxygen double bonds, right? So the aldehydes, they have the carbon oxygen double bond, and then that carbon that's double bound to the oxygen has a hydrogen on it, right? Ketones, carbon oxygen double bond with carbons on both sides. Carboxylic acid has the hydroxide group, and hydrides are like ethers, only they have two double bond oxygens on those carbons that are sandwiching the oxygen in the middle. And esters, again, like ether, only just one of the carbons has a double bond. Amides, carbon nitrogen, that carbon that's bound to the nitrogen is double bonded to oxygen. Okay, so that, but all of these have that same characteristic, that the carbon that makes up the functional group has a double bond to oxygen. And then whatever else it's bound to makes it these different families, whether it's hydrogen for aldehydes, another carbon for ketones, hydroxyl group for carboxylic acids, and etc. And then the final one is, the final three families are functional groups that contain sulfur in some role, right? And like I said, these are important in are important biologically, particularly with our proteins. Okay, so I think that does it. That wraps up our intro to chemistry. And let's get out of here. Why isn't it exiting? That's strange. There we go. That's it. So hopefully this made some sense. And if you have any questions, please feel free to bring them up to me during lab time, or after journal club in the afternoon, or shoot me an email. Feel free to reach out to me in whatever avenue works best for you. Okay, take care. I'll see you next time.